Hey guys, today we're going to talk about a different type of reaction, oxidation and reduction reactions. It's not even really a different type of reaction. It's just a very specific way of looking and examining the reactions we've already taken a look at. And specifically, we're looking at what's happening with those electrons. We've got a couple of words. First off, today we're going to learn what do oxidation and reduction mean, and then how do we identify oxidation numbers on atoms or ions. So go ahead and get those reference tables out. If you don't have it out right now, go ahead and push pause and then grab the reference tables and come on back when you have it. All right, so when we're talking about oxidation and reduction reactions, the very important detail is they involve a transfer of electrons. Oxidation used to mean a reaction that had something reacting with oxygen. So in iron rust, it's being oxidized because it's reacting with oxygen. But now it means something a little bit more specific. An oxidation reaction is going to involve the loss of electrons. Right? What that means is the charge or the oxidation number is going to get larger because remember those electrons have a negative charge. So if something loses an electron, the charge or the oxidation number gets bigger. When something gets reduced, the reduction is that charge is getting reduced. When does it get reduced? When something is gaining electrons. This is a little bit confusing if you think about it from a gaining electrons is reduction, but remember the charge or the oxidation number is getting reduced. We have a phrase, a couple of them. You can use Leo says grr, right? Losing electrons is oxidation, gaining electrons is reduction. Just one way we have to memorize which one is which. All right, so what are oxidation numbers in the first place? An oxidation number is usually very similar to the charge of an atom or an ion. It catches some molecules when they don't have a charge, we can still use this oxidation number term. This is a way of an accounting system for the electrons. When something is gaining electrons, its oxidation number goes down to indicate that it's gaining electrons. When it's losing electrons, the charge goes up, and so we have the oxidation number increase. If it's an ion, it's just going to be equal to the charge of that ion. If it's an atom, it's just going to be zero. So a couple of rules. First off, free elements. An element that is not in a compound is going to have an oxidation number of zero. If you have a monatomic ion, so it's just an ion all on its own, that's gained or lost electrons, the oxidation number is the same as the charge. If we have a compound, compounds are neutral. So overall, the oxidation numbers will add up to zero. If we have a polyatomic ion, ions do have charges. The total sum of all the oxidation numbers of all of the pieces of that polyatomic ion will add up to the charge of that polyatomic ion. We have a couple other rules. Hydrogen is always going to be +1. Oxygen will always be -2, except for peroxides, like hydrogen peroxide you'll find in your cabinet at home. Then oxygen is a -1, but for us, the oxygen will always be -2. Halogens, like your chlorines and fluorines and bromines, are usually going to be -1. The only catch is if they are with a more electronegative element, such as oxygen. Sometimes the halogens are a little different, but the halogens are usually -1. And the group 1 and 2 metals are +1 and +2 respectively. Something you'll notice, we tend to write charges with the symbol after the number, like the charge of an oxygen ion would be 2-. We say the oxidation number with the charge first, so -2. If you get those backwards, everybody knows what you're talking about, but we try and stick to the right mechanism. Okay, so what does that leave behind? It leaves behind mostly the transition metals and a couple of the other nonmetals like carbon, sulfur, and nitrogen, which have a lot of different possibilities. On your reference table, you'll notice in that periodic table, they have selected oxidation states as one of the details in the top right-hand corner of each box. And so that's one other hint we can use when we're trying to figure this out. So again, why are we looking at the oxidation numbers? We're trying to see if atoms are gaining and losing electrons during a chemical reaction. And the oxidation numbers help us figure that out. All right, so here's a couple of examples. These are about as straightforward as we can get. Assign each element an oxidation number. So magnesium and oxygen in choices A and B, these are free elements. In general, these are the easy ones, but we tend to overcomplicate things when we're learning. but these easy free elements are going to be a 0. So each magnesium, or that magnesium atom, will have an oxidation number of 0. And in the molecule O2, it is an element, so each oxygen has an oxidation number of O2. It's nonpolar, it's not gaining or losing electrons. Choices C and D are what we will call monatomic ions. It's one atom that's gained or lost electrons. So choice C, the oxide ion, would have an oxidation number of -2, and the sodium ion would have an oxidation number of +1. All right, so when we have compounds or polyatomic ions, we want to figure this out, and one method we use is something called an each total column. So we can make a chart like this underneath the compound, underneath the chemical formula, and then we have a row for each and a row for the total. What we mean by that is in a molecule of water, there are 2 hydrogens and there is 1 oxygen. So we can look at each hydrogen first before we look at the total from all of the hydrogens in that compound. So how are we going to do this? We label the oxidation number for each atom with the rules we just learned, and then we calculate the total by multiplying the oxidation number by the number of atoms in the compound. Also, we want to make sure that the total row adds up to the total charge of all of the particles, 0 if it's a compound, or the charge of any polyatomic ion. Here we see that hydrogen had a rule of +1 each, but there are 2 hydrogens in that formula, so we multiply the +1 times 2 for a total of +2. The oxygen is the only one in this compound, and oxygen is always a -2 for its oxidation number. So that's the same for each in total because there's only 1 oxygen. And then if I add a +2 and a -2, the total row adds up to 0, and water is a neutral compound, so that makes sense. The oxidation number for hydrogen is +1, and oxygen is -2. Here's 3 other compounds. If we look at them, we'll start with E, magnesium chloride. The magnesium, the each, is going to be +2 because it's a group 2 metal. Chlorine would be -1 because it is a halogen. So we have a +2 and a -1 on the top. Then underneath here, we're going to go ahead and fill in the total. So there's only 1 magnesium, so +2. But because there's 2 chlorines, I will double the -1 to -2. And so those all add up to 0. In this potassium nitrate, we don't know the nitrogen. We don't have a rule for nitrogen. So we're going to come to that last and use a little bit of an algebra. So potassium is going to be +1 because it's a group 1 metal. The oxygen is going to be -2 each because it's oxygen. And then nitrogen, if we don't know it, what do we use in algebra when we don't know something? We often just call it X. So I would put an X here for the each box for nitrogen. Now, how do I fill in the total column? If you're writing this down on your own paper, why don't you go ahead and figure out what you might write down in the total column? All right, because we have 1 potassium, I would take +1 each, +1 total. There's 1 nitrogen, so +X total. And then oxygen, we've got -2 each, but there's 3 of them, so that would be -6 total. So now I can look at this, and I have an answer here on the next slide I'll get to. We have +1 plus X -6, and that all has to add up to 0. So what value for X will give us a total of 0, and that's how we figure out that nitrogen should be a +5. Now in this last example, we have sulfate, which is a polyatomic ion. We've got sulfur. We don't know that, so we'll plug in an X for sulfur. Oxygen, we know is a -2 each, but there are 4 oxygens, so that would be -2 each, but -8 total. So I would have X -8, but it's not going to equal 0 because this has a charge. It's going to add up to a -2. So X -8 equals a -2. X must be +6. And so we can see here, I can move my face out of the way of the answers. We've got the nitrogen would be a +5 and the sulfur would be a +6. If we had 2 nitrogens or 2 sulfurs, we would total that up to 2X on the total column on the bottom. All right, and that's all we have. That's how you do it. That's how we figure out the oxidation number for any atom in any compound or any ion. This will take you through the first lesson, And in the second assignment, we're going to look at an entire chemical reaction. So just giving a preview of that, here we have a couple of different chemical equations. We've got an A magnesium plus Cl2 makes MgCl2. So what we look at is a first-year chemistry student, that trap mistake is going to be looking at the magnesium and just putting it down +2 both times. But on the reactant side, magnesium is an element and chlorine is an element. So magnesium here would be 0, chlorine here would be 0. Then in the compound, magnesium has changed to +2 and chlorine has changed to -1. So the oxidation numbers are changing, which tells us we've had a transfer of electrons. And then we can do that with a number of different equations, and we can really just get real crazy with this if we wanted to, but we'll probably keep it simple here for the first week. And there you have it. That's all you need to know for assigning oxidation numbers, and then we'll be able to identify when we've had an oxidation reduction reaction. All right, that's it. Good luck, and see you next time.